Um, so I am from SMU, as you, you all heard. I hope everybody's safe, and those who are joining us remotely are seeing everything and hearing everything fine. So today's talk is about the role of machine learning and data analytics in advanced simulations of geotechnical systems. So basically, I'm going to touch on two things. One is advanced simulations of geotechnical systems, what that is, and how can we use it, and data science. There is no question that data science is an emerging field, and with the big data that is around us coming from so many sources, there must be clever ways to analyze these data and extract information that is not usually easily to see in using regular and traditional visualization tools. So briefly, this is the outline of the presentation, go through introductory about the motivation for this work and an example of this advanced modeling techniques. Here we call it SPHDM technique. I will explain that in a minute. And then my area of expertise is mainly earthquake engineering, geotechnical earthquake engineering. So I'm going to talk about the response, seismic response of level and sloping ground as an example of a problem that is so complicated and the need of advanced simulation techniques. And then we look at data science, what data science can offer in this case to analyze the enormous amount of information that we get from these data. And not only that, I'm going to also extend the use of this technique to another very complicated problem of a ground that is a saturated soil that is overlain by an impermeable crust. And we're going to see what is the impact of that crust on the top will have on the response. And then apply again data clustering to everything we have and see what kind of information we get. And then I wrap up with conclusion. So when we say advanced simulation, I mean, we're talking mainly about these type of new trends that can handle large strain effects on the behavior. And these are typically needed for extreme conditions like earthquakes, flooding, where sometimes the mainstream tools that we have, such as finite element and finite difference techniques, implemented in very useful and popular software like FLAC and Praxis, for example, just to name a few, may not perform very well and can involve a lot of approximations. So the drawback of this advanced simulations is that they produce enormous amount of data. And you cannot just ignore the fact that this data may have some useful information. The reason is we always try to process these data using the common knowledge we have that we have acquired over the years. So we have a certain predetermined aim. We want to look at stress strain, that's all. But we don't want to go beyond that because it's so difficult. But that's the usefulness of using things like what we are going to look at today, is that maybe there are more information that is useful there. So we discovered some key relationships that are in a problem like soil liquefaction that we are going to discuss today. And we can look at different stages of liquefaction and how it can be different depending on the slope itself, whether, or the deposit itself, whether it's a level slope, a level or a sloping ground, or in the presence of an impermeable crust on the top. Really, this is an ongoing research, I must say. It's funded by the NSF and some resources coming from the Corps of Engineers as well. So the main objective here is not only to visualize the data, which we will see today, which is very useful. I hope you will agree with me about that. But also, what we are focusing on is that this enormous amount of data need enormous amount of storage. And very often when we run these simulations, we cannot really save everything. It's just too much. So we would like to have an online algorithm, if you wish, that tells us when and where in the system to save data so we can have an efficient way of storing data and, processing them later on. So SPHDM scheme, what is that? So basically, we look at the soil system, saturated granule material. That's what I have been studying for now more than 20 years. Is like at a very detailed scope. We try to look at the soil as a collection of individual particles. So imagine that you have granule materials like sand, and I'm modeling the sand at a grain level. On top of the sand, of course, or the void is in this case is full of fluid, water, if you wish, and we need a model for also modeling fluid. Now you can model this fluid at different scales, ideally to match the idea of modeling the grains at grain scale, or the particles at grain scale, is to model also the fluid in the inside the pores. And that can be done, and I have worked in this area, but as you may imagine, these are significantly difficult and computer and time consuming. So a little bit less time consuming scheme is to have some average fluid points, like these blue points that you see. So they work on the average behavior of a collection of particles rather than what is happening in one single pore space. So basically, what we do for the granule, for the soil particles, is we use this technique called discrete element method, DEM. That's for the solid phase, for the grains, and smooth particle hydrodynamics for the fluid phase. We couple both of them using some interaction relationships that can make each phase see the effect of the other. I don't want to go through many equations, but quickly, this discrete element technique is really very simple in concept. Just we simplify the grains, even though you can actually have them as irregular shape nowadays. But in this particular study, we simplify them to just spherical particles. And at the contact, the whole modeling thing is at the contact. There are springs and dashpots to model the force displacement law. And then once we have a definition of these contact stiffness and dashpot properties, we can get forces at the contact. So each grain will be acted upon by so many forces, and then we solve Newton's second law of motion to get new particle position and rotation. So when you look at this equation quickly, I'm sorry, there's this term. This is the term coming from the interaction from the fluid, and that is now coming from the smooth particle hydrodynamics. It's a little bit interesting technique in the sense that we define a kernel function, and we use some density kernel function to describe that, and we can retrieve from that function the properties that we're interested in. In this case, we can get pressure and velocities as well. And then we define a solid fluid interaction using an equation that is responsible for momentum exchange between the fluid and the particles. So let's start first by doing a simulation, and then we discuss data science application. This is a soil deposit, saturated soil layer, grains, as we discussed. Because the system is so similar everywhere in the lateral direction, we only separate part of it. So we study this column, and we use a technique called periodic boundaries. That's a numerical technique that makes these lateral sides repeated everywhere in the lateral direction. We use also some other concepts because, as you can imagine, even with grains that are of the size of sand, you can end up having millions of particles. So we use a technique very common in geotechnical centrifuge studies, like applying high G level to increase the level of stress, but at the same time benefit from scaling laws. So we get to shorten the heights and the time of the simulation. Here in this particular study, we use particle sizes very close to coarse sand sizes, between 1.5 to 2.5 millimeter. And these are the properties that we got. And at the same time, we have this fluid that is filling the voids. We apply seismic motion to the base of the deposit here. In this case, we just apply very nice sinusoidal motion so that we don't complicate the response too much by applying a random quick motion. But we can if we want. So again, we have so many results coming from any single simulation, but to focus on is key things, key mechanisms. So I know we are in Dallas, we are in Texas. We don't really worry much about something like soil liquefaction, but it's interesting to at least understand what happens here, because the idea is to learn how an advanced modeling like this can capture a complex phenomena like liquefaction. So liquefaction is a phenomenon that, to simplify its definition, it takes place when a saturated loose sand soil is subjected to seismic shaking. In that case, during shaking, because of the tendency for this loose sand to densify, the void space is trying to reduce. So by squeezing the void space, pool pressure starts building up, pushing back the grains. Now, if the pool pressure generation wins, meaning it's capable of pushing back the grains enough, then you will end up having these grains separated, and you will end up having grains that is essentially floating. So you can imagine now your soil that was supporting a foundation turning into basically a soup. Of course, anything that is supported on that soil will sink, collapse, and significant lateral deformation can happen if there is mild slope even. So it's a very dangerous phenomena. Usually it takes place in areas where there are high seismic areas and of course, saturated loose sand that is near the surface. So with this simple definition, here is the input motion at the base, and what we compute is the excess pool pressure ratio. Now, if that excess pool pressure ratio is the ratio between excess pressure, excess compared to hydrostatic, initial hydrostatic pressure, divided by the initial effective stress. If that excess pressure approaches the initial effective stress, again, that means your soil is essentially floating. So that is represented here by this pool pressure ratio of 1. Once you see this line, this excess pool pressure ratio approaching 1, it means now you have liquefaction and you have this instability phenomena taking place. And that's what is happening almost over the entire deposit in this case. This is more of the same thing, but looking at profiles of pool pressure building over time. And again, here, we even plotted the effective stress, the initial effective stress that so we can see how the increase in excess pool pressure is progressing to match the initial effective stress. Post shaking, pool pressure starts to dissipate and goes back to hydrostatic. This is how the acceleration, if we record the acceleration at different depth locations, that's what we got. So when the soil liquefies near the surface, you don't see any acceleration because the particles are essentially floating and there is no way for the motion to be transmitted. This is a very interesting parameter that we don't get from our mainstream tools like finite element and finite difference or continuum models. This is a coordination number. This is a micro scale parameter. It describes the average number of contacts per part. And the interesting thing about that, you need at least 4 contacts to have a stable package. Anything less than 4, then it means you have an unstable system. And by looking at this, it looks like indeed, once liquefaction took place, this coordination number started to drop below the value of 4, which is needed for stability. Stress strain, we are all aware of what stress strain indicates. So the solid stiffness, basically. So the reddish line indicates the early stages of shaking, and then as it gets more blue, it means the later stages. And you can see here how the stiffness degraded as time passes and liquefaction took place. If we do the same thing on a sloping deposit, just a mild slope, we get pretty much very similar trends with key differences. You notice here the pore pressure ratio, even though it approaches 1, it does have significant spikes that we did not see in the level deposit. The reason why for these spikes is because when the soil is moving upslope, it tends to dilate, and when it dilates, it basically tries to absorb water, so it reduces pore pressure. It gains a little bit of stiffness and reduction in pore pressure. Acceleration, it doesn't completely die, as we have seen in the case of level ground. Again, you see here these negative spikes. These are very common. Anyone with knowledge of response of these systems and have seen centrifuge tests will agree that this is something that we see typically in sloping ground simulations where we have these negative spikes, which happen again when the soil is moving upslope because of dilation. But liquefaction here of this sloping ground caused a lot of lateral deformation up to about 60 centimeters by the end of shaking. That's significant, as you may imagine. Stress strain, because of the liquefaction and because we have a slope, you have tendency to accumulate very large strains reaching near the surface something in the neighborhood of 15%. That's significantly large strain. Now, what data clustering can help us? This is a typical, pretty much data processing that we have been using in mainstream tools like finite element or finite difference, and we try to mimic that using the output from our simulations. But we have so much data, we have so much information. Can we use data science tools to understand them? So that's what my colleagues in the business of data science started working on. And we looked at several things. We looked at the raw data, and from the raw data, we can extract a trend, a first derivative, which is delta, and a cyclical response, which is the high frequency component of the raw data. This is a sample of this data processing. So in the case of level ground at this particular depth of 2.4 meter, we have acceleration. This is raw acceleration. This is raw coordination number, and this is raw pore pressure ratio that we have seen in the slides before. Each one of them will start getting trend, derivative, and an envelope. This cyclical response is an envelope in every single parameter of these. So we looked at acceleration, correction number, pore pressure ratio, volumetric strain, shear stress, and shear strain. We did the same thing for the slope. And of course, this is only for one depth. We repeat the same concept or data processing for every single depth location. Now, this is a starting point, a combined feature correlation plot. Here, we combine the level and sloping ground data. And what we notice is that in this diagram, the way you read it, this at any particular location, you have the name of the variable, This is the poor pressure ratio at the very bottom to the left, the poor pressure ratio trend. And then you start moving all the way up to the poor pressure ratio delta. Now, the way you read this diagram is it gives you a correlation coefficient between the variable and at any given location if you read it horizontally and vertically. So for example, in this case, we had the correlation going from 1 to -1. 1 means positive correlation, and -1 means negative correlation, meaning when something is going up, the other parameter is going down. So as an example to reading this data, if you look at the very bottom, poor pressure ratio trend, you have a negative 0.76 right there in the bottom row. And that is this poor pressure ratio trend of negative 0.76 is the strongest or highest compared to the coordination number trend. So these two parameters were strongly correlated but in opposite direction, meaning that if poor pressure ratio decreases, then correlation number will increase and vice versa, which of course makes sense, but that's how this diagram and these numbers are read. And then we go from there to grouping all the parameters. We have so many of them, and then but some of them are closely related from this first step, and we can group them. In this particular study, we realize that they come back to like 7 groups, 7 distinctive groups, and we start plotting them in this diagram. So we have 7 distinctive zones, regions. This is how they vary with time. The horizontal axis is time. These vertical lines that you see here, the first 5 seconds of shaking, because the signal was going up gradually. And then from 5 to about 12 seconds, you have a constant signal, and then it goes down again by the end of this point at the right. Now, what we notice, these color-coded zones represent distinctive features. Each one of these colors possesses a distinctive feature that was very pronounced in every case. So you can say in the level deposit, the top figure, we see a red, blue, green, orange, and then brown. When we look to the cluster number 6, which is yellow, we don't see it really on the top. But this cluster 6, it was very clear near the base of the sloping ground. Now, what are these clusters? What is distinctive about these clusters? We can learn that from cluster profiles. So again, you notice that you can say that red is pre-liquefaction, blue is liquefaction, full liquefaction. And then after that, it's how the system is behaving during liquefaction itself. So pre-liquefaction, we notice that the most pronounced feature in this zone was the shear strain, the trend and its delta. And then now, once liquefaction takes place, coordination number has the strongest trend, and as well as the cyclic component of the coordination number. In this green area, we have shear strain and volumetric strain. And then in this magenta area, we see that poor pressure and poor pressure ratio are the ones that are distinctive to this magenta area. In this orange area, you notice that we have the coordination number variation, the derivative, and the variation in poor pressure ratio. In the yellow area, which was only for the slope, we notice shear stress was the most pronounced, shear stress and acceleration was the most pronounced feature in this area. And then in this brown area towards the end, we notice that acceleration again goes back up, and coordination number and volumetric strain start to increase. So this is what we call clustering of the different behaviors that we have in the data and try to tell us what every single time zone and as shaking progressed was what was the most distinctive feature. Instead of just looking at a two-dimensional plot, it tries to combine everything that we have in basically one single figure. We can also do something called a principal component analysis, or PCA. So we analyze the data and we start seeing what is given by the explained variable value. We analyze everything we have. We have 12 distinctive features. And we notice that the highest ones are PC1 and PC2. And when we apply these principal components, PC1 and PC2, against each other, we get a plot like this. This is now, doesn't look very clear because it's for everything we have, all data, all depth, level, and slope. So maybe a better feature is to separate things a little bit. So here we have the level and sloping ground side by side at a particular depth, 2.4. So what we see on the left in these diagrams, we see these arrows. Their magnitude and their direction have a meaning. The magnitude, of course, relates to how strong the effect of this parameter is. And also the direction tells us is the relationship between a particular correlation or how a particular parameter correlates with another. So if the two arrows are like this, it means there is strong positive correlation between, in this case, correlation number trend and pore pressure ratio. And if there is one arrow that is completely out of phase with another parameter, it means that there is correlation, but the correlation is almost a -1 correlation that we have seen in this case. So not only that, we can also see this progression of these zones, that color-coded zones. So in the level ground, we see first red, and then blue, and then green, and then orange, and then brown. Now, the reason why this stops here is because we did not process everything until the end, like during the dissipation phase. We only analyze things during liquefaction. But if we do, we're probably going to see this loop is closing. The same thing here in the sloping ground. Another way of processing this data to see the separation between these distinctive groups is to do this UMAP, or Uniform Manifold Approximation and Projection. And again, this is everything of the results we have. The dot is the sloping ground and the X is the level ground. Now, every group, you notice there is really separated group. It's just like a confirmation that these distinctive 7 clusters are really separated. They do tell us a distinctive feature compared to the other things. That's what the usefulness of this analysis is does for us. So we want to examine how this also does this work really for more complicated cases. So we performed other simulations where the same saturated deposit is overlain by an impermeable crust. So the same deposit, but we put on top a 1 meter of impermeable soil, like clay, silt in real life. Very common scenario, by the way. It turns out, even though it may look at the first glance that this shouldn't be a big deal, but actually it is. The reason why is this impermeable crust is non-liquefiable soil. It is not going to liquefy. There will be no build-up pressure there. But the soil underneath is liquefiable, but its water is being trapped only inside this column and cannot get out anywhere. So pretty much the same data, except for we added this crust that is imposing a stress of 10 kilopascal on top. We carry out the simulation. This is snapshots of how this deposit looks like, deformed shape, if you want to have the similarity. Now, what's happening here is that as shaking progressed, this granular soil is reducing in volume because that's what shaking does. It densifies the soil. The consequences of this is the formation of a water film, a gap between the granular soil and this top impermeable layer, a water film. This is significantly dangerous. Your soil, anything there now is not really being founded on grains. It's founded on water. It's supported by water. And the interesting thing about these results, so this is the effective stress profile, the red line, and you notice it starts on the top with a value of 10, which is the magnitude of the imposed crust stress. As pore pressure builds up, it picks up these 10. So water is carrying the weight of this crust, and that continues during shaking and post shaking. By the time 30 seconds, which way after shaking stops, pore pressure goes back to this vertical value. This vertical value now is not zero. It's constant and equal to 10 kilopascal, which is the weight of the crust. Kind of expected. If our technique is working, it says that this really working because this is what we expect. If this doesn't bother us in the case of a level ground, the situation becomes significantly dangerous in the presence of a slope. So in the case of a slope, these are also snapshots, but for the sake of visualization, we colored this middle portion of the deposit black, so we can tell how does the lateral deformation looks like. Now notice what is happening. Significant large lateral deformation is taking place where? Only at the size of few grains at the interface between the granular soil and the impermeable crust. Not only that, if you pay attention to how this impermeable crust is laterally moving, it's moving very large displacement, even separated from the trend of the underlying soil, like it's behaving on its own. And if we want to focus more, even though it's not as pronounced as in the case of level ground, but also there was a water film there. And basically particles here are moving down slope at very large displacement. It's not new. We have seen this stuff again in centrifuge testing, and it's a very complicated thing. And now if you want to analyze this computationally or predict it computationally, it's extremely hard. Because you're looking at the scale of very few grains to ensure that really there was complete separation between this crust and the underlying soil. We print these contacted chains, the contact force network between the soil and the top of the crust, the top crust. So in the beginning, before shaking, there was very strong network, very healthy network supporting the crust. But then as soil liquefied and this water film developed, there is no contact. This thing is on its own, and it's moving downhill in like a free fall, if you wish, sliding, just sliding. I don't want to repeat the trends that we have seen before, but the most distinctive behavior of this simulation was the fact that near the interface between the granular soil and the impermeable crust, significant volumetric strain developed because of the formation of that water film. And of course, significant shear strain developed as well. So we took every data, all data, the ones from the level ground and sloping ground with no crust, and then the data coming from the new simulations with crust, slope and level, and combined everything and started clustering them and see how many distinctive features will appear. And what we observed is that instead of the initial 7 that we had, that just finished their data science work, there was an additional zone, 8, this lighter magenta color, if you wish. And it's here, near the surface of the slope with a crust. This was another distinctive feature that was not observed in the level ground with or without crust, or the sloping ground without crust. This light magenta color only happened in the case of this impermeable layer. And if we look what is so distinctive about it here, oh, it's marking significant volumetric strain, shear strain, which we know that, but it's very interesting to see that there is a tool that can capture that from our data. It gives us confidence that this technique is actually working. Because what we want to do now, is if you wish, even though this is advanced technique, it's really, we are applying it on, if you wish, one-dimensional problem. It's just a soil deposit. But if you have now much more complex system, like an actual slope of a dam or a soil foundation system or sheet pile or retaining walls, meaning things are not now one-dimensional anymore. The fact that we can have a technique that can extract this and tell us where we have failure zones or shear bands or large deformation, it's quite interesting, quite interesting. So in conclusion, I have presented a glimpse of what we call advanced modeling of geotechnical systems. And the reason why this is interesting is that it's seamless. Seamless in the sense that it can model the system without change in input. So all the simulations that I have presented, the 4 of them, are done with exactly the same input data. This is not common if you do finite element modeling or finite difference modeling. If you use Plaxis or you use FLAC, you know that every time you need to tweak few things. Oh, needs to be a little bit modified, a little bit fine-tuned. Here, not, because we're trying to go as fundamental as possible, trying to base our modeling on first principles with less room for empirical assumptions. So, with the different liquefaction pattern discovered or liquefaction state, this clustering can be used in classification to explore feature importance or to perform prediction tasks that classify unseen soil deposits based on these relationships. We leverage this observation pattern and relationship while considering the overall purpose of simulation and data mining to help simulation researchers with knowledge discovery. And as I mentioned in the beginning, really our next goal is to take this one step further to build an online data-driven learning model that can classify liquefaction stages and focus on interesting and unexpected behavior encountered in real time, meaning while the simulation is running. Thank you very much for your attention, and I will be happy to answer your questions. I just have to give credit, of course, to my colleagues, Dr. Michael Heisler from the Computer Science Department and his student, Ethan, and my PhD student, Saman Farzi. Of course, he has done all these simulations. Yes, sir.
First question, we now set up a model. Are you saying that it's an anisotropic, homogeneous structures, soils?
It is isotropic in the sense that there is no reason why the soil will be anisotropic. We can have it anisotropic if we have, let's say, irregular grains. We can have that. It is not perfectly homogeneous, though. I mean, if we look at the distribution of porosity, it is not constant everywhere just because of the way we generate this deposit. We generate it the same way as we generate an experiment. We pour the grains in a container, so there is no way that we can maintain exactly the same packing everywhere.
And have you ever tried to identify certain regions of the world, down in New Zealand and Australia, that had some earthquakes there that caused some liquefaction to occur, and all of a sudden it is now within hours of now in the floodplain. And I wondered if you've been able to use your modeling situation here in a real world application to identify that soil structure.
I haven't, because I cannot right now, with the computational resources I have, to model exactly the same grain by grain. It can be done, though, with some approximations, but I haven't done that. It doesn't mean that this technique is not validated. I mean, of course, I don't have time to show that. This is a very complex technique. It's very difficult to do one-to-one kind of comparison. So we kind of separate the problem into pieces. So we can verify dry soil alone. That has been done. And we can verify a coupled problem, but let's say it's a regular array of arranged particles full of fluid. We have classical analytical solution for that. We were able to retrieve things like that. A particle settling in a jar, we were able to verify that because, again, we have experimental data for this, and we have also analytical results from Stokes law for these kind of things. We verified that we can get these things, so we validated our model using what we call a building block. So instead of validating the whole complex problem, we break it into pieces, and we validate each piece. Of course, there is still, of course, a room for a a global interaction, if you wish, for the whole system, but this is hopefully the next step. Any other question? I don't know if the people online have questions. I cannot tell.
Yeah.
I don't know. Not see even the icon for some.
But they can hear us.
Okay, I don't. I was trying to see if audience online.
I didn't see any on my phone.
Oh, so okay, so we're checking.
Okay. Nope. We're
Okay.
having some audio issues at first, but it got resolved in a minute.
Okay, great. Thank you so much.